Good morning, students. Audio video is okay.
Yes, sir.
So, in last class, I have taught you the basics of the simplex method or simplex algorithm to solve the linear programming problem. And over that, we have done some good question. In continuation of that, let us have this question. The following table represent a specific simplex expression. Means this is not it is not given that it is initial table or the final table. It is any table. All the variables are all the variables are non-negative. So whatever the condition of LP problem that is given to you, the table is not optimal for either the maximization problem or minimization problem. So this table is not a optimal table for any kind of the problem. Thus, when non-basic variable enters the solution, it can either increase or decrease z. So depending over the non-basic variable, which one will be the entering variable. So if it is the question of means if it is the question of maximization, then that variable has the capacity to increase the value of the z. If it is the problem of the minimization, then that variable has the capacity to decrease the value of the z or leave it unchanged depending on the parameters of entering non-basic variable. So now you have to so this is the table. So categorize the variable as a basic variable, non-basic variable, provide the current value of all the variables. So in this case, as I have told you, always we write the basic variable on the left side. So for this table, you can say that x8, x3, x1 are the basic variable, and corresponding values are 12, 6, and 0 respectively. So it will be the non-basic variable. X1 will be the non-basic variable because no, because N1 in the X1 is the in the basic pool. So here X2 is the non-basic variable. X3 is also in the basic variable. So X4 is the non-basic variable. X5 is the non-basic variable. X6 is non-basic variable. X7 is non-basic variable. Whatever the sequence of the X8, X3, X1, in that sequence you can observe it is forming the identity matrix. Right. So never change the sequence of the variable. So here in the first part, so basic variable are x8, x3, x1, and corresponding values are 12, 6, 0, and the value of z will be the 620. Value of the z is 620, and all others variable are non-basic variable x2, x4, x5, x7, and you know that always the non-basic variable at the 0 level. Always all the non-basic variable are at 0 level. Now in the B part, assuming that problem is of maximization type, identify non-basic variable that have the potential of improvement of the z. So which non-basic variable has the potential to improve the value of the z if it is of maximization problem? It is given to you that if it is of maximization type, then which non-basic variable has the capacity, has a has a characteristic to improve the value of the z. So as I've told you, in the maximization, no optimality condition is what we have to check the which one is the most negative. It means the Z coefficient corresponding to x2 are, are negative, corresponding to x1 is negative, and corresponding to x6 is negative. It means the very non-basic variable x2, x5, and x6 have the capacity to improve the solution if problem is of maximization. If each such variable enters the basic solution, determine the associate leaving variable if any and associate change in Z. Do not use the Gauss-Jordan row operation. So it is they are saying that if x2 is the entering variable, presently we are not saying that most negative should enter. We are not performing the simplex method, right? So if x2 is entering, so we take the ratio 12 upon 3 right hand side, right hand side and right hand side value and element of the entering column. So 12 upon 3, 6 upon 1, and this ratio is not possible because this entry must be the non positive. This entry must be the positive. Similarly, corresponding to x5, so here we have, so no corresponding to x5, here we have the 6 upon 1 and 0 upon 6, right? 0 upon 6. So these two are the valid entry, right? These two are the valid entry. Here we these two are the valid entry. Now, in case of the x6, in case of the x6, here we take the ratio, so 12 upon minus 1 not possible, 6 upon 0 not possible, 0 upon minus 4 not possible. So here we will not get any leaving variable. So here it is written, if x2 enter, means in the B part the x2, x5, x6 will improve the solution because the z coefficient are negative. So in case of the maximization, if Z coefficient are negative, then the problem has capacity to improve the solution. Clear? Wherever you feel any confusion, please stop me and then ask. So in this case, now if x2 enter, we take the ratio minimum of 12 upon 3, 6 upon 1, and this ratio is not possible. So so after the row operation, x2 will take the value 4 and x2 take the value 4, and here the z coefficient is the 5. So total change in the z value, 620 will be the 5 into 4. So now in the next iteration, if x2 enter, it will increase to the 640. So due to entry of the x2, there is the increase in the value of z by 20. So delta z will be the 4 into 5. Similarly, if x5 is what? If the x5 is the entering variable, then we take the ratio. So first ratio is not possible. Second ratio is the 6 upon 1 and 0 upon 6. We take the minimum. So minimum is the 0. So when the x5 will enter, so here the z coefficient is the minus 1. Here the z coefficient is the minus 1. So in this case, the total change will come 1 into 0, that is the 0. Means it will z will remain 620. Z will remain 620. Then x6 enter. If the x6 enter, then you are not able to take any ratio, right? You are not able to take any ratio because the element of the entering column are either negative or 0. So in this case, you cannot take the ratio. It means there is no leaving variable. There is no leaving variable. So here you can see actually what is the meaning of the leaving variable. What is the meaning of the leaving variable here? As I've told you, in case of the simplex table, What is the meaning of the ratio? Means if any line, let us have this line, this line, this line. So what is the minimum ratio? Means you are computing this intersection point. You are computing this intersection point, right? From the ratio, you are getting the intersection point. Minimum is the closest point. If you recall the graph of the simplex method, in that here we have the 4 comma 0, and here we have the 6 comma 0. So we have taken the minimum this one, right? From the 24 by 6 we have taken this, and from the 6 upon 1 we have taken this. So this is the optimal, if you recall the first table of the simplex method of the redeeming problem. So so when there is no living variable, then when there is no living variable, it means there is no intersection, there is no intersection in that line. It means in that direction, you can increase your value up to any extent. In this direction you can increase your value of the x1 up to the 4 only. But when there is no intersection, right, there is no living variable, that implies that you can increase the value of the z up to any extent, up to the infinity also. So due to the infinity, the value of the z will become infinite. From the 620, the value of the z will become the infinite. Clear this part? No living variable, and x6 can be increased to infinity, so delta z will be the infinity. Clear this part? Now repeat part B, assuming the problem is of minimization. So when the problem is of minimization, so here what will happen? The variable whose z coefficient, the variable whose z
Sir,
coefficients are positive has the
sir,
capacity. Yes.
so can you please repeat the part where you calculated delta Z?
Please speak little louder.
So
क्या
can you please
what?
repeat the part where you calculated delta Z?
Okay. Here I am saying that minimum in this part, when x2 is entering, minimum of the all ratio is equal to 4, and here the z coefficient is the 5. So total change will be the 5 into 4. Total change will be the 5 into 4. So that will be the 20. And means in the next iteration, the value of the z will be the 640. The value of the z will be the 640. If x5 is entering, then the change will be here the eh, x5 is equal to 5, and there z coefficient for the x5 is the -1. So in this case it will become 1 into 0, that is the 0. So it will become the 620 plus 0, that will be the 620. And here, since x6 has a no, for the x6, when x6 is entering, there is no living variable. No living variable means there is no bound for the x6. You can increase the x6 up to any extent. So as you increase the x6 up to any extent, the delta z or z will become the infinite.
Got it, sir. Thank you, sir.
Now repeat the part B, assuming that problem is of minimization. So when the problem is minimization, we take the positive z coefficient. Positive z coefficient, and for the entering we decide with the most positive z coefficient. So here the non-basic variable which has the positive z coefficients are this x4, right? So x4 has the capacity to improve the value of z in case of the minimization problem. So in case of the minimization problem, x4 can x4 can improve the solution. So when x4 will enter, then the ratio will be, 12 upon minus 2, not possible. 6 upon 3 is equal to 3. 0 upon 0, not possible. So only one ratio we take. So that is the 6 upon 3, that is equal to 2. So when the x3 will leave, then the delta z will be the 4 into 2, right? And that will decrease. So delta z will be the minus of 4 into 2, minus of the 4 into 2, that is the minus 8. So now, so you can see here x2, x x2, x5, x6 have the capacity to improve the solution in case of the maximization problem. X4 has the capacity to improve the solution of the minimization problem. And but x7, but x7, right? X7 is also the non-basic variable, and its z coefficient is equal to 0. Its z coefficient is equal to 0. So it has the capacity to enter in both maximization as well as the minimization problem. And so as shown in B, x5 cannot change the z because it enter the solution level at 0 level. X7 cannot change the z either because its objective coefficient is equal to 0. So delta z will be the 0 into minimization of the 12 upon 5, 6 upon 3 and dash. So I'm saying that when x7 is entering, so ratio will be the 12 upon 5. This ratio is feasible. 6 upon 3, this ratio is possible, and this we cannot take. So 0 into minimum of 12 upon 5, 6 upon 3, right? Delta z will be the 0. So due to the x7 and x5, there is no change. If x5 and x7 is entering. So in the last part, they have asked this only: which non-basic variable or variables will not cause a change in the value of the z when selected to enter the solution. Clear this part? Clear this part?
Yes, sir.
So when we are solving, for example, this is the table of the minimization problem. This problem we have already solved. So this is the minimization problem. So here you can note in the minimization problem, as we proceed the iteration, right? Here the value is z, here the value is minus 32, here the value is minus 80. Means continuously it is decreasing. Iteration by iteration, it is decreasing when problem is of minimization. When problem is of maximization, the value of the z, right? So this is the optimal table for the ready mix. So here the value is 21. So this is the intermediate table. Here the value is 20, and this is the initial table. Here the value is 0. So you can see in case of the maximization, as we proceed, right, in the iteration. So from the first value 0, right, it increased to the optimal value 21. So 0, 20, 21. So that is the case of the improvement. Now, next question. Consider the following LP maximize 16x1 plus 15x2 subject to 14x1 plus 31x2 less than equal to 124 minus x1 plus x2 less than equal to 1, x1 less than equal to 3, x1 x2 greater than equal to 0. Solve the problem by the simplex method where the entering variable is the non-basic variable with most negative z coefficient. This is the usual method. If it is the maximization problem, then always we take the entering variable whose z coefficient is the most negative. That is the rule. Now they are saying that resolving the problem by the simplex algorithm, always selecting the entering variable as the non-basic variable with least negative z row coefficient. Now they are saying that in the simplex method algorithm, you change, instead of taking the most negative, now you take the least negative as a entering variable. Then what will happen? Compare the number of iteration in A and B. Does the iteration of the entering variable as the non-basic variable with most negative z coefficients, z row coefficient lead to a smaller number of iteration? What conclusion can be made regarding the optimality condition? Suppose that the sense of the optimization is changed to minimization by multiplying the z by the minus 1. How does this change? They are saying that if you select least negative instead of the most negative, then what will change? So here, when uh, when the most negative, so here the z coefficient z row will become the z minus 16x1 minus 15x2. So most negative is what? Minus 16. So when the x1 will enter, you start from the A, you have to proceed to the B, then you have to proceed to the C, then you have to proceed to the D. So in case of the most negative, the sequence is the A, B, C, D. If you select the least negative, means if you select the least negative, means x2 will enter. So when x2 will enter, so you have to go A to E, then E to D. So here, in case of x2, this is in case of the x1. In case of the x2, it will be the sequence will be the A, E, D. So we can observe that doing choosing the least negative, will give you the less number of iteration, but it is by chance only, right? So here x1 will enter first and the iteration will follow the path A, B, C, D. When x2 enter means least negative. Least negative. When you take the least negative, x1 enter means most negative. When you consider the most negative, then this will happen. Least negative first, then the iteration will follow the path A, E, D. So most negative criteria requires the more iteration. This criteria is only the heuristic, although it does not guarantee the smallest number of iteration. Computational experience demonstrate that on the average, the most negative criteria is more effective. There is no rule, right? Might be choosing the least negative can give the answer optimal solution in the less number of iteration, but experience says that in the most of the cases this is computationally more effective or efficient. So we choose the most negative. So now they are saying that in the last part, suppose the sense of the optimization is changed to minimization by multiplying the z by the minus 1. Should this change affect the simplex iteration? So they are saying that now instead of the this objective function is the minimization z is equal to minus 16x1 minus 15 x2. So z row will become z plus 16x1 plus 15x2, and we take the most positive. We take the most positive. So they are saying that is there any change in this? So naturally there is no change. So that is written here, that iteration are identical, means in when we select the most positive, then then the iteration points are a b c d. If you select the least positive, then iteration points are a e d, with the exception of the objective row, which should appear with the opposite sign. Now, just to brief the simplex method, I have chosen this question. Just to do any step, there should not be any problem. Yes,
Excuse me, sir.
yes, yes.
Sir, while solving for the maximization, when we find out the ratio, we see for the least ratio which we are getting, right?
Huh?
So, similarly, in the case of minimization, why are we looking for, while finding out the ratio, we are also looking for the least ratio which we are getting. Shouldn't it be
Huh?
the positive? Sir,
No, no.
I mean,
Actually, why we are taking the least ratio? That's why I have done that example. Na? For example, if you recall the ready mix problem. Okay, first I show the graph of the ready mix problem. If you recall the ready mix problem, see, here we have the graph of the ready mix problem. When x1 is entering, which variable will be the leaving variable? So this is the line of s1 is equal to 0. This is the line of s2 is equal to 0. Clear? So now, if x1 is entering, we take the ratio 24 by 6 equal to 4, 6 by 1 is equal to 6. This ratio is not possible, this ratio is not possible. So minimum is this one. Minimum is this one. So when we take the minimum, at that time, you are taking the closest intersection of x1 with s1 or s2. So it means it guarantee the feasibility. If you take, instead of the s1, if you take the s2, that will give the infeasible.
sir,
Right?
this was the case for maximization, right? I'm
No, no,
talking about minimization.
actually, no, no, minimization or maximization only when we increase the value of the z. When we increase the value of the z, that is only the things. Right? Means here we have the z is equal to 21. Or when we decrease, then it will decrease. But feasible region, what about the feasible region? Feasible region is due to the constraints only. So for the constraints, we take the minimum things, then only you will get the closed region. Na?
Okay, sir.
i'm
Thank you.
i'm saying that if you have the closed region like this, so either you increase the z or you decrease the z, you decrease the z, you decrease the z, you decrease the z. That is another thing. That is the minimization and maximization, another thing. But when we are making the closed region, then you have to take the minimum ratio, right? Then we have to take the minimum ratio. Then it will be the closed region.
Okay, sir. Thank you, sir.
For that purpose, I have done one question also to show this. I think this one. But if you are not taking, the x1 as an entering variable, instead of that, if you take the x2 as s2 as a leaving variable, then automatically you can observe here we will get the infeasible solution. Clear? So
Yes,
for
sir.
to explain that question, I have done this question. Any other doubt? Now last question from this. In example 3.3.1, so how the second best optimal Z can be determined from the optimal table, right? So if optimal table is given to you, this is the optimal table. If optimal table is given to you, can we determine the second best solution? Second best solution. So exactly what we are doing, you know that this is the optimal point. This is the optimal point, or right, optimal point, or you can say optimal table. From the optimal table, can we determine the second best solution? So it means you are propagating in the back direction. You are propagating in the back direction. So either you go in this edge or you go in this edge. So how we can do the same procedure? Whatever there is the entering variable, that will become the living variable. Whatever the living variable, that will become the entering variable. So with that, you can recognize the second best. So in this case, here we have the optimal table. So if S1 enter, if S1 enter, right? Presently, this is the optimal table. So because it is the positive, it is positive. There is no negative. So it is the optimal table. So by now, here the x1, x2, x3, x4 are the basic variable. They are the basic variable. They are the basic variable. Non-basic variable are s1 and s2. It means that that can enter. Non-basic variable can enter. So we choose if s1 enter. If s1 enter, the ratio will become the 3 upon 1 by 4. If this ratio is not possible, 5 upon 2 upon 3 by 8, 3 by 8, and this will become the 1 by 2, 1 by 2 upon 1 by 8. So now we choose the which one is the minimum, right? So here we take the minimum of 3 upon 1 by 4 dash 5 by 2 upon 3 by 8, 1 by 2 upon 1 by 8. So minimum is equal to 4. So when the minimum is equal to 4, so what will be the change? Change will be the 3 delta z will be the delta z will be the 3 by 4 into 4, 3 by 4 into 4. So that is equal to 3. So the value of the previous table, value of the previous table, then the this optimal current optimal table will become the 21 minus 3, 21 minus 3, that is the 18. Now if s2 enter, if s2 enter, if s2 enter, so we take the ratio. So this ratio is not possible. Here we have the 3 by 2 upon 3 by 4. This ratio is not possible. This ratio is not possible. So here we take, so its value is equal to 2, s2 is equal to 2. So the change will be not 2, I think, yes, 2. So delta z will become the half into 2, half into 2, that is the 1. So it will be the 21 minus 1. So that is the 20. So second best will be the 20. Second best from the 21 is the 20. So it means in the previous table, S2 S2 is the basic variable. So from the optimal table, immediate preceding table you can generate. Immediate preceding table you can generate. Now the last part, can you
But
extend the procedure in
how are we?
problem 9 to determine the third best optimal value of the z? So can we determine the third best optimal value? So as you have seen, we have proceeded from the 0, 20, 21. A right? A, B, D, C. So 0 in the simplex table of the ready make. First table give the z is equal to 0. Second table is the z is equal to 20. Third table is the z is equal to 21. So second best we can compute. Now the question arises: can from the 21 we can generate the table for the z is equal to 0? So no, you cannot generate, because we do not know from where we have the value 20, right? So here not exactly extended, because the third best solution may not be the adjacent corner. Actually in the simplex method we move to the corner to corner, right? From means corner to corner or adjacent to, over the edge. That is the simplest algorithm. Always we start from the origin, we move to next best one, right? Next best corner through the edges. So always we can move from corner to corner, never we can jump. If we have the graph like this, so from here first we move to here, then we move to here, then we move to here, right? Or we can move directly here, right? But we cannot move directly here, so that's why we cannot determine the third best. If by chance it is not a means adjacent corner, if it is the adjacent corner, then in some cases we can find, but we cannot generalize that. Yes, one is asking
Sir, which one variable will leave
S1.
in the ninth question? Which variable will leave?
Means S2 variable will enter.
Yes, sir. S2 will enter. Then who will leave? What is the procedure for
X2,
that?
X2 will leave. See, this is the optimal table. Here the variables are X1, X2, S3, S4. So this is the same table, right? Here you can see X1, X2, X3, X4 are the basic variable. So this is the optimal table, and this come from the this table X1, S2, S3, X4. So here we have the that part. This table you have to determine. So that is the z is equal to 20. Clear?
Sir, from the optimum table, we can't tell that S2 is leaving.
Actually, they want from where this 21 is coming. Either the 0, 20, 21 or 0, 18, 21. They want to ask this.
Okay,
So,
sir.
uh, if you proceed in the reverse way, so you can note here the in the second table. Optimal table is the third table for the ready make problem. Optimal table is the third table. So in the second table you can see S2 is the basic variable and X2 is the non-basic variable. So when X2 enter, S2 will be the living variable. Now they are saying that can we proceed in the reverse manner? So yes, you can proceed in the reverse manner, but only in the immediate corner, not to the third corner. That is the conclusion of this question.
Excuse me, sir.
Yes.
So we can conclude that uh, while plotting the graph, we cannot tell either we will go in the one direction or in the reverse direction, because since we saw in the question number 8, it is not compulsory that least negative number may have the most maximum number of iterations, right?
Huh, huh, huh.
So by like you showed from the graph of the readymake problem, if it had been another question, so by plotting the graph, we won't be able to tell either we will go in the reverse direction or in the forward direction.
No, no. Actually, it is Let us have this graph. So what is the simplex iteration? Always start from the origin, then move toward the maximum improvement from corner to corner through edges. You have moved to this. Let us have this is the optimal point. Now the question arises: this optimal point come from this point or this point, this point or this point. So so means in the at this point you assume that basic variable are x1, s2, s3, s4, and at this point basic variable are x1, x2, s3, s4. It means this is the combination of leaving and entering variable. Now that they are saying that make it as a leaving variable, make it as a leaving variable, make it as a entering variable, make it as a entering variable. You will get the previous table from the optimal table.
Sir, if the optimal point would have been one above this, which you have mentioned, sir, like first, sir, जहाँ वो
A,
ऊपर,
B, C, D, E,
yes, sir, if it would have
F.
been D,
It
if the
हाँ बोलो.
optimal point would have, if the optimal point would have been D,
हाँ
फिर तो हम E वाली डायरेक्शन से भी जा सकते हैं और C वाली डायरेक्शन से भी जा सकते हैं. I guess E
हाँ.
would be better because the number of iteration would be less.
By that is by chance. Actually, there is no proof of this that most negative will give you minimum number of iteration. There is no proof of this. This is only the heuristic. But now this heuristic we have made the convention. Because by solving so many questions, 1,000 questions, we have observed that by taking the most negative, we will get the minimum number of the iteration. In one or two question, you can get the some contradictory result. But in maximum question, you will get the minimum number of iteration by choosing the most negative one. So it is only the heuristic, no proof of this.
Okay, sir, thank you.
In this question, if I'm saying that s2 is the entering variable, s2 is the entering variable, x2 is a leaving variable, just you have to make it 1. As you make it 1 and this as a 0 by the Gauss row Jordan method, you will get the exactly the second table of the ready-mix problem. Clear? So procedure is the exactly same. So from my side, simplex method is over. In next class, I will start. Presently, we have the 5 minutes, but in next class, I will start the new topic. But all are very important topics. So in this, I have chosen so many questions just to clear the concept of the minimum ratio, optimality condition, feasibility condition, entering variable, leaving variable. Still, if you feel any problem, you please tell me. So from my side for today, it's over. If you haven't doubt, you can leave.
Thank you, sir.
Welcome. Ayushi Jain, please speak what you want to say. Ayushi,
Good morning,
हाँ
sir.
हाँ हाँ.
Sir, actually, due to addition and substitution, my lecture section has been changed to L1, but my tute section is still T2. So, like, is it fine?
No, no, you attend the then tutorial of the L1,
Okay,
T1.
sir. But sir, my
So
name
that you
is
will not,
registered over here.
it will not affect any
Okay,
test or any things, right?
okay,
But it will give you the continuous lecture.
Okay, sir.
So
So,
you
sir, is
attend
it
the
fine?
tutorial of, from our side there is no problem.
Okay, sir.
You attend the CB madam tutorial then.
Okay, sir. Thank you.